Good afternoon, everyone. Today we're going to begin our study on regression diagnostics. So what does this mean? We have after we have constructed our model, our final model, using different regression techniques, it's not enough that we're able to interpret the results, interpret the meaning of your parameters, the meaning of your betas, okay, and its marginal effect on your dependent variable, all things being the same. So we have looked at that. We have looked at the details of how to interpret our parameters. It's not enough that we have our final model. It's not enough that we have our mathematical model. We have written the model. In our case, we were looking at hourly wage and its relations with some of our uh, predictors. Okay, it's not enough that we have the final model and interpret the meaning of the coefficients. What we have to do is to test the validity of our model by doing regression diagnostics. We have to test if yung model natin, if our model is consistent with the assumptions of classical linear regression. Okay, so let's have our discussion now. Okay, I'm going to load these packages that we have been using uh, several times already: tidyverse, psych, hmisc, this task, OLSRR, car. Okay, and some I think I didn't put here, which we're going to load later. Okay, so let me just load these packages. And then, okay, let's have a review of the regression diagnostics. Let me share this with you, class. Control C. And let's go to this site. Oops. Let me chat this. Okay, let's have a quick review of the assumptions of classical linear regression. Let me open this. And in your case, kindly open this too. Okay. So we have here, this is an economic theory blog. Although medyo may pagka-mathematical to, but it's okay. There are other sources by which you can look at the at the assumptions. I like this because it's it involves some math, and it also involves some practical discussion. Okay, number one is the first assumption. Wait. So it just gives a short introduction to the assumptions of classical linear regression model. And we said that for a classical linear regression model, the OLS method is used, ordinary least squares. Okay. Okay, you can, if you want to see the derivation, you can click this. Okay, and it is founded on the Gauss-Markov theorem. Okay, the Gauss-Markov theorem espouses that the best estimators of a model involve the computation which gives us the least squares of the residuals. Okay, so a let's say attribute of this Gauss-Markov theorem is that the least squares estimator are unbiased, no? And have minimum variance. So itong minimum variance na to, class, uh, this now is the homoscedasticity assumption. Dapat yung residuals natin, they should be constant. Kasi pag hindi na constant yung residuals, hindi na magiging minimum variance yan. Okay? So you can have several unbiased linear estimators. Okay? You can have several combination of estimators, and they may all be unbiased, but there's only one that has minimum variance. Yung minimum variance yan, class, yun yung ano natin. That's the what we call the blue, no? That's part of the blue. What's the blue? That's the best linear unbiased estimator, no? So the Gauss-Markov theorem is telling us that in a regression model, the expected value of our error terms is 0. This one we have discussed. Sabi natin, if we get the mean of the error terms, 0 yon. It should be 0. And the variance of the error terms is constant and finite. Yan. Okay, the sigma squared, the variance of your error terms is equal to a certain number, sigma squared. And this is less than infinity. Okay, finite siya. Okay, and also your error terms, epsilon sub I and epsilon sub j are uncorrelated. Okay, and we said that this is not so much of a problem for cross-sectional data kasi ang cross-sectional data naman, yung order does not matter, di ba? Problem yan, malaking issue yan kung time series yung data. Kasi yung data, pag time series, it follows a certain arrangement na hindi pa pwedeng baguhin. Sa cross-sectional data, it doesn't matter kung i-rumble natin yung data, no? Mababago yung ano no, yung linearity ng correlation ng epsilon not residuals natin, no? Okay. So yung sa classical linear regression model, yung OLS, okay, based on the Gauss-Markov theorem, yung parameters natin B0, yung slope at saka intercept are unbiased, as we said, and have minimum variance. Okay? So if you want to look at the proof, mathematical proof, tingnan nyo na lang yan. Alright? So this is what I mentioned a while ago. Okay? Ito yung assumptions ng Gauss-Markov theorem. Okay? So that the estimators will be blue. It's the best linear unbiased estimator. Okay, so the assumptions are dapat linear yung parameter and correct dapat yung model specification. Ano ibig sabihin ng correct model specification? Yung model natin dati, di ba, hourly wage is a function of education plus ano yun, experience, etc. Ang assumption nun dapat correct yung specification natin. What do I mean by correct? Okay? Ibig sabihin, wala nang missing na ano na predictors, or ibig sabihin yung education natin as a predictor is correct. Ano ibig sabihin ko nun? Kasi pwede yung education, pwede palang education squared. Alright? Kasi pwedeng hourly wage is regression education plus education squared. Di ba pwede, pwede yung x natin, yung mga independent variables, pwede siyang ano, pwede siyang naka-square, pwede siyang naka-log, pwede siyang naka-1 over. Pwede yun. In OLS, pwede siya. Okay? Walang restriction dun sa sa independent variables. Dapat hindi siya squared o hindi siya naka-log o hindi siya naka-square root o hindi siya naka-cube. Pwede, class, pwede. Ang sinasabi natin linear in parameters, yung mga betas natin, hindi pa pwedeng naka-square, naka-cube, no? Sorry. Pero yung mga predictors natin, pwede yan. Okay? Then we have this full rank ng X. Okay, I'll leave this class for your own perusal kasi medyo pupunta tayo sa linear algebra ng konti, no? But I hope you spend a little time to study ano ibig sabihin ng full rank of matrix X. Yung matrix X is your matrix ng mga predictors. Okay, then explanatory variables must be exogenous. Ano ibig sabihin ng exogenous? Dapat yung mga predictors natin, hindi siya yung pinipredict natin. Okay? Ang pinipredict natin yung dependent variable, yung endogenous ang tawag natin doon, endogenous variable. Okay? So yung mga ano natin, yung mga predictors, yung mga independent variables, hindi siya yung pinipredict, no? Ibig sabihin, given yung mga yon. Okay. So, independent sila. Okay? Tapos, number 4, yung error terms, which I mentioned a while ago, dapat independent sila. Okay? And normally distributed also. And number 5, ito, yung normal distribution ng error terms. Okay, I will not class look at the discussion. I will leave you for you to yourself to look at the assumptions. No? Okay. All right, so let's go back to our R. Okay, so last time we also looked at this, sinummarize lang natin to, no? Linearity of the data, okay, linearity of the parameters, and then this one class, this is taken from the initial file that we had. Ito yung homogeneity of our residuals, dapat constant yung variance ng residuals natin, residual variance, hindi pa pwede yung non-constant. And yung multi-collinearity, dapat yung mga independent or explanatory variables natin, hindi siya dapat collinear. And also, yung residual, sabi natin, hindi dependent. Dapat independent sila, hindi dependent. Okay? And we said that this is an issue more for time series, normality of residuals also. Okay? All right, so we're going to take a look at this. Let's first import. We have already done this in the past. So import ko lang si wage. Dinelete ko siya kanina. So I'll just run the first one. Hindi ko na kukunin yung structure. So we have done this in the past. Okay, there's a question here. Okay. Iaano natin Glenn yung ano, no? We will thank you Glenn for that question. How do we remedy kung may multicollinearity? We'll discuss that one by one. No? Anong gagawin natin kung heteroscedastic yung residuals natin? Maraming remedies, no? And we'll discuss that when we go to that individually. Okay? Ano din gagawin pag may multicollinearity dun sa mga independent variables natin? But very good question, and thank you, Glenn. We'll discuss that, no? Okay, so I just converted the categorical variables into factors kasi baka errors lang later, no? So I'll just convert this. Okay, and if we now take a look at the structure of wage, it will now say that our categorical variables are now factors. And we know the default of R as far as the benchmark or reference factor. Okay. All right. So what we did last time was to create a model where we regress hourly wage on all our predictors. Okay. So let me just run this. Okay. Sabi natin, ito yung regression output natin where we have here some of our predictors that are not significant. And what we learned last time was if we perform stepwise regression, we'll be able to come up with the final model. So here, I'm just doing the stepwise, okay? So this is from OLSRR. So I'm using the backward fit.p. That's just a name of the object. Pero ang function na OLS step backward p. Okay? And I'm using the model here. And P remaining is equal to 0.5%. All right, so if I run this, which you ran already before, it shows us what are the living variables. No? Kasi backward to eh. So ang unang tinanggal si race, tapos si number of dependents, tapos si experience. Okay? So out of these 7 variables, 7 out of the 7 predictors, 3 were removed. So ang matitira na lang 1, 2, 3, 4. Apat na lang matitira, no? So I just run that, no? Dito rinan ko siya. So let me just overwrite the model. Model is LM hourly wage, regression, education, tenure, gender, civil status. Data is equal to wage. Okay, so these were the 4 remaining variables. No? Tinanggal natin yung 3. Siguro next class, next meeting, pag-uusapan natin yung one last sa regression, no? Yung disadvantage ng stepwise regression. Okay, kasi ang stepwise regression, it just considers one variable at a time. So that can be a disadvantage. No? Although dun sa OLSRR, diniscuss natin dati yung all models, yung sabay-sabay lahat, no? Kung 5, kung 6, kung 7, ano yung pinakamagandang model. That's what I meant, no? All right. So with that, okay, we now have this. This is now our final model. And we already learned how to interpret this. Okay. So let's now test. So we can now develop the equation for this. Hourly wage is equal to negative 2.16. I'll just put the two decimal places, plus 0.53 times education, plus 0.15 times tenure, plus 1.771 times gender, minus 0.69 times civil status. Okay, so that will be our plus epsilon sub t. Okay, that will be our model. And we said that based on the ANOVA here, F stat, p-value is practically 0. So the overall goodness of fit test is that the model is okay. All right, so we also learned last time that based on this, we can do some residual plots about our model. All right, so let me just share this with you, just the text. Then I want you to write the code for that. All right, so we will just partition our plot. Okay, matrix format, rows 2 by 2. Okay, so we'll plot it 2 by 2, and then let's plot the regression model. This will generate 4 plots, which we said there are actually 5 plots that's generated. Okay, so the first one is residuals versus fitted, and then scale location, and then we also have residuals versus leverage and the QQ residuals. Or we can use the from ggplot to the autoplot function. Okay, same plot class. Okay, same plot. Residuals versus fitted, scale location, residuals versus leverage, and normal QQ plot. Actually, we learned before that this actually has how many plots? If I write plot, and then mod, which is equal to 1. Let's just review this quickly. So this is the first plot, right? Residuals versus fitted. Fitted. The next one, number 2, is your QQ plot there. The third one, which is equal to 3, is your scale location. And then the fourth one is, okay, so this is not shown in the function here, plot mod. Okay. What's shown is 1, 2, 3, and then 5. Okay, so this is the residuals versus leverage. Okay, and let's see if there's still another one, 6. Okay, yeah, there's a 6. 6, no? Okay. May 6 pa pala class, I'm sorry. Nalagay ko lang yata dito 5. So there should be 6 here. 6. Wala nang 7. Okay, yung 6, it's related to number 4, yung Cook's distance versus leverage. All right, so let's look at them one by one. Sorry. Okay. In the interest of time, let me just share with you the text class. Let me just share with you the text so that we'll just focus on the code. Okay, the first plot class is residuals versus fitted. So what do you find here in this plot? This one. Or we can so you can run this code class. The plot mod which is equal to 1 and run this. So this is the residuals versus fitted. Okay, so for this plot, actually there are several things that we can learn here. We can learn here about the linearity of the relationship between your dependent and independent variable. We can learn here also about homoscedasticity, okay? And we can learn here also about outliers and influential points. So itong plot na to, class, it gives us several information, and I wrote it here, class. This is a scatter plot of the residuals on the x-axis here. Sorry, on the y-axis, and then your predicted values or fitted values on the x-axis. Okay, so predicted versus the residuals. Okay, so scatter plot siya, and it's used to detect nonlinearity, unequal error variance or residual variance, which is heteroscedasticity, and also outliers. So itong first plot na to, tatlo yung nakikita natin kagad dito. Okay, so unang-una, sorry, kung sana, class, kung dali lang, class, ha. Okay, sorry about that. My problem is when my cough starts, tuloy-tuloy siya, no? Nagtutuloy-tuloy. Okay, so you can see, class, the line, and ideally dapat yung red line na yan dapat horizontal. So it's following the trend of your, I'm sorry, class, of your residuals, no? Hold on, class. Okay, but in this case, you can see that the red line does not display a horizontal line. Of course, it may not be a perfect horizontal line, pero ito makikita natin na ano, may difference siya. Dito, yung mga fitted values natin up to this point, medyo it follows a downtrend. Pero dito bigla nang nagpataas, no? So makikita natin dito na this tells us about if maybe a problem with the linearity of our linearity ng natin, ng relationship ng data natin, no? And then same thing, kung horizontal, kung medyo horizontal line to, it tells us about the distribution of the residual, yung variance ng residuals natin. Ito kasi sabi natin, di ba, pag may trend siya, tsaka may fanning out, eh. So a clear indication that our residuals, homoscedastic yung variance ng residuals natin. And also, ito, may mga in-identify na 59, 15, at saka 229. This identifies outliers, no? So, pwedeng hindi magka-issue yung outliers, which we'll be discussing in a while. All right? So, sabi natin dito, sa makikita natin, a well-behaved residual has the following characteristics, no? Yung line niya should be around the zero line, okay, to indicate that the relationship is linear. Dapat horizontal siya, no? Para homoscedastic yung error variance natin, and dapat walang gaanong outlier, no? Dito may mga konting outlier na identify na to, no? So dun sa first plot pa lang, we can see three possible problems, no? Yung linearity, which is the first assumption. Tapos yung homoscedastic dapat constant variance, mukhang may problema. And also yung outliers. Okay. All right, so there is a linear relationship between the predictors and the dependent variable. Yun ang sabi natin, di ba? Yun yung yung linearity assumption natin. Okay, so we can take a look at, we looked at the visual representation, and we can see that medyo may violations of linearity dito. Okay? Then we can also plot what we call a component and residuals plot. Okay? So ito hindi pa natin na-discuss dati. Also known as partial residual plots. So let's take a look at this. I don't think I shared this already with you. Okay, isama ko na to Okay, hanggang sa dulo na. Control C. Kasi medyo ano tayo sa oras no? Oops, ayaw. Babawasan ko lang class. Pagtulong ayaw ni ayaw ni Canvas. So just copy up to this one. Control C. Okay. Now, as I said, there's a function from the car package. Okay. Pwede natin gamitin yung component plus residual or the partial residual plots. So, ginagamit ito similar to the plot which is equal to 1 kanina for checking the linearity assumption of the predictor. Okay, so let's run this class. Itong CR plot na to from the car package. We don't need to load this kasi this comes preloaded with R. Itong car, no? So if we run this class, there. Okay, makikita na dito yung relationship ng hourly wage natin with the independent variables. Okay, sa hindi naman masyadong problema dito sa categorical kasi hindi naman natin ma-relate correlationally yung categorical variable with the dependent variable. Makikita lang natin dito na may mga outliers. Okay? There are outliers here. Pero dito class, ito makikita natin. Okay? So between education and the this is the component plus residual hourly wage, no? We can see here that mapapansin natin dito na may trend. Okay? Dito din may trend. Okay, which tells us that hindi constant yung dito, yung CR, yung component plus residual, which tells us that there might be a problem with the relationship between your predictor, education, and your hourly wage. In fact, na-test natin to, di ba? We measured the correlation, it's only 0.4. Ito 0.3 lang yata. So talagang medyo weak yung correlation ni education at saka ni hourly wage and also tenure with hourly wage. Okay, but this can be addressed, no? Pag may mga ganyang problems in correlation, in linearity, that can be addressed. Okay, one way to address this is pwede yung data natin, let's say yung dependent variable natin, ita-transform natin. Okay, we can transform that. But we'll address the remedy next time na lang, no? For now, anuhin muna natin yung yung mga assumptions. All right, any questions with this so far, class? Any questions with this? Kindly chat please kung clear naman so far. Okay, how about the others? I'm getting a few responses. I would appreciate, class, your feedback. Especially, class, medyo hindi talaga maganda yung pakiramdam ko. Okay. Okay, so thank you so much, class. I appreciate your immediate feedback. Okay, so I share this also with you, class, no? Sabi natin, if the relationship is linear, the points in a component residual plot should be randomly dispersed along a horizontal line. Ito, ano? Randomly dapat, kaso ito may pattern, no? Kita nyo, di ba? May pattern siya eh. Habang lumalaki education, tumataas yung ano, yung CR, yung yung values ng ano ng CR. Diba? Okay? Si tenure parang reverse naman. Although si tenure medyo mas ano pa nga, although may there's a parang nagka-cluster sila dito, no? Si tenure. Okay, thank you. Okay, if there's a presence of a distinct pattern, like yung sa ano, yung sa education, di ba? Merong pattern na lumalaki siya, no? It's increasing. Okay? It indicates that there are potential issues with the linearity assumption of that predictor. Kasi 'di ba sinasabi natin na dapat linear yung relationship ng predictor na yan at saka ng ano ng dependent variable. Okay? Tapos sinabi natin it can also be used itong CR plot to determine influential data points. Okay? Later on we'll discuss what outliers or influential data points are. So yung influential observations which I mentioned before are very critical because their presence radically changes the regression model. Or ang reversion, pag tinanggal siya, malaking pagbabago ng regression model. Okay, that's what an influential data point does. All right, so I hope this is clear yung unang plot natin. Now let's go to the scale location. So I deliberately chose the number 3 plot muna. Okay? So ito number 3 plot class. Ang pinaplot natin dito is the square root of the standardized residuals. Okay, yung residuals, ibig sabihin, ni-normalize siya. Ginawang standardized, which means yung residuals, you subtract the mean of the residuals divided by the standard deviation. Yun ang standardized residuals and then kinuha yung square root. Okay? And then the fitted values, parang yung kanina, fitted values versus residuals sa number 1. Dito naman, square root ng standardized residuals versus the fitted values. Okay, so ano naman to? Ito class, it helps us check. Also outliers, ito, may outliers naman dito, and yung heteroskedasticity. Okay? Paano natin masasabi kung heteroskedastic? Practically, parang horizontal line, itong red line na to. Kasi yung red line na to, sinusundan niya yung trend ng ng residuals natin. Okay? So here, makikita natin na there seems to be an upward trend. Kitang-kita naman, no? May fanning out. So this tells us that chances are our residuals are heteroskedastic. Okay? Na-violate yung assumption natin ng homoskedastic dapat yung residuals natin or yung residual variance natin should be constant. And here are also outliers. Sorry class, may mali ako dito. This is a case dapat to. A case. Okay, so let me once again share this. So apologies class for ayaw. Wait lang. Bawasan ko class. So ano ba yung shinare ko? So let me share my notes here with you. Ito lang muna. Control C. Tulong na naman. Ang iksi lang yan ah. Okay. Ayan, sige. All right, and then let me share the next one. Okay. All right. So we we discussed this a while ago, yung scale location natin class, no? All right. And then uh, let me just explain to you class what's the consequence if the residual variance is not constant, if it's heteroscedastic. Ano mangyayari? Now, we said that one of the assumptions of classical linear regression uh, is that the residual variance should be homoscedastic in order for us to generate yung dun sa OLS natin, ordinary least squares, it should be the best linear unbiased estimator. Blue siya, no? Blue. So, according to the Gauss-Markov theorem, the least squares estimator for our B, okay? Ito yung parameters natin, unbiased yan. Okay? If we follow the assumptions of Gauss-Markov, unbiased siya plus. Ano ibig sabihin ng unbiased? Minimum variance yan. Okay? Which is what we need. Unbiased. Pag biased class, hindi na ano, hindi na siya yung ano, hindi na siya yung yung minimum variance. Tapos because of that, hindi na siya efficient. Okay? So if it follows or if it does not violate the assumption of the classical linear regression model, it will have minimum variance. No? Kasi nga, homoscedastic yung variance natin. Okay? Assuming it fulfills the Gauss-Markov theory. Now, pag heteroscedastic siya, class, ano mangyayari? Ano mangyayari, class? Yung, okay, take note. The betas class, the betas, okay, pag heteroscedastic, hindi naman magiging ano, hindi naman magiging bias yung estimators natin. Okay, please take note of that, no? So, pwedeng ano pa rin siya, unbiased pa rin yung estimator natin. However, okay, and this is very important, I carefully chose my text here. If it's heteroscedastic, ano mangyayari? Magkakaproblema sa pag-compute natin ng variance covariance. Okay? And because of this, what happens? Yung standard errors natin, magiging mali. Okay, if you recall, sorry, wala yung ano ko, hindi ko makita yung ano ko. If you recall class, di ba dun sa, okay, sige, balikan natin yung ano natin, yung summary. I'll go here just to bring home a point. This one, class, ito. Okay, di ba ito? So may estimate tayo, no? So yung estimate daw natin ng parameters natin, hindi naman nag-i-introduce ng bias dito. So unbiased pa rin to. Ang problema natin, class, itong standard error natin. Okay? The way this is computed, kung meron, kung heteroscedastic yung residuals natin, magkakaproblema tayo dito sa pag-compute ng standard errors. Okay, so what will happen if the estimate is okay, unbiased siya, pero yung standard errors, mali na. So what will happen is that the t-value will be inaccurate, no? Kasi yung t-value natin is based on the estimate divided by the standard error. So if you recall, class, our t is equal to your beta divided by your SE, your standard error. So kung mali itong t-value, class, kung medyo hindi na siya accurate, di mali na rin tong mamamali itong p-value natin. Kasi the p-value, if you recall, di ba, is based on the t-value. Okay? So ito related tong dalawang to. Kung mali yung t-value, pwede mamali tayo sa natin, probabilities. Okay? And all because kapag heteroscedastic yung residuals natin, ito nangyayari. Nagkakaproblema sa pag-compute ng standard errors. Okay? All right. Let me pause for a while, class, and chat nga. Paki-chat please kung naintindihan so far. Okay, good. Thank you. Okay, good. How about the others, please? Okay. Don't worry, class. Hindi na natin papakita mathematically na may problema, magkakaproblema sa variance sa standard errors, ano? Okay. Pero ang importante sa atin, alam natin theoretically, but not necessarily uh, com computing it statistical wise. Hindi naman tayo stat majors, no? So ang importante sa atin yung yung implications ng heteroscedastic na residual variance. Okay, so as I mentioned here, class, okay, so kapag heteroscedastic, class, nagkakaproblema tayo sa pag-compute ng variance, covariance ng residuals natin, and hence magkakaproblema tayo sa pag-compute ng standard errors. So mamamali yun. And it leads us to wrong t-statistics and p-values. So the implication is that, okay, one cannot compute the t-stat and the p-values correctly. And consequently, baka inaccurate yung hypothesis testing natin. It might become not possible na, di ba? Kasi mali na eh, di ba? Mali na yung mali na yung standard error natin. Mali na yung t-stat natin. Mali na yung mali na yung p-values. Mali na rin yung 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 inference natin. Hypothesis natin magiging questionable. Overall, under heteroscedasticity, OLS loses its efficiency and hindi na siya blue. No? Hindi na pwede yung best linear unbiased estimator. Okay, naging inefficient na tayo, no? Kasi possibly yung natin, yung residuals natin, hindi na yan yung minimum variance. Okay? Sabi nga natin, unbiased pa rin yung data natin, no? Yung coefficient natin, unbiased yan, walang problema doon. Pero yung estimates natin, pwedeng hindi na siya efficient. Alright? Unbiased siya, pero hindi na siya efficient. Anong ibig sabihin ng hindi na efficient, class? Yung residuals natin derived from the estimates are no longer the minimum variance. Assumption niya ng Gauss-Markov, dapat yung variance natin, yung residual variance natin, dapat minimum yan. No? Should be at the minimum. Alright, so now there's a good reference for this. This is a PDF file. No? So buksan nyo nga, class, and then ang suggestion ko, basahin nyo to, no? I-load nyo to. This is a very good reference. Okay, PDF file siya. Okay, na-download ko na yan. Pinakuha sa PDF ko. Ayan, nandito siya, class. Alright, so tingnan natin very quickly. No? This is all about, this is from Berry and Feldman. No? May book si Berry and Feldman. So sinummarize dito, no? Sinummarize dito. So it explains what heteroscedasticity is. Okay, so this is an example of your residuals not being constant. Okay, ito din, hindi constant yung residuals. Okay, so ano yung consequences, class? Okay, this is a very important point, class. Yung heteroscedasticity, pwedeng pwedeng byproduct, or it can be caused by another cause, no? These violations have their own consequences. Okay, so it can be a byproduct of other violations of assumptions. So pwedeng baka yung nonlinearity ng natin, ng data natin, nagko-cause siya ng heteroscedasticity. Okay? Ito, class, no? However, OLS estimates are no longer blue. Take note, ha? Hindi na siya yung best linear unbiased estimator. Okay? Sabi nga natin, among all, kasi pwedeng maraming iba't ibang combinations ng estimators, no? Hindi na siya nagbibigay ng the smallest variance, hindi na yung minimum variance. Okay? So, as we stated a while ago, significance test can be too high or too low, yung mga p-values natin, based on the t-stat. So, the reason OLS is not optimal when there's heteroscedasticity, it is that, ito, class. Very important to. When you compute for the variance class, yung observations equal yung weights nila. Okay? So ibig sabihin may mga variance na may mga residuals na napakalaki, no? Tapos may mga residuals na napakaliit. So ang ginagawa doon, equally weighted lang pag kinompute natin yung variance. 'Di ba pag naalala niyo pag kinompute natin yung variance, say let's say we're taking a look at E, no? It's equal to E minus the mean of E, di ba? Squared over n minus 1. Okay? So yung n minus 1 na yon is the divisor for all the excess residuals, you know? E minus E mean. Right? So equally weighted sila. Okay? So one way to address yung may heteroscedasticity is mag-weighted least squares. Ibig sabihin, yung malalaking residuals, liliitan natin yung yung contribution nila sa pag-compute ng beta. We'll discuss that class when we look at the the remedies, no? Okay. All right. So, I'll leave you guys kasi dito ang ginagamit dito yung state, no? Punta tayo sa R kasi R yung ginagamit natin. But for text, for theoretical discussion, you can refer to this. Okay. Balik na tayo dito. Kita niyo to class, WLS. This is weighted least squares. This is one remedy pag heteroscedasticity. Kanina tinatanong ni Glenn, ano yung remedy kung may multicollinearity. Mas madali yung remedy doon, class. Mas mahirap yung remedy ng heteroscedastic yung residuals natin. Okay, let's first test, class. Kasi ano lang tayo di ba? Visual lang tayo. Mas maganda kung visual at saka statistical yung test natin. So we can make use of this one. From the CAR dataset package, we have this non-constant variance test. Okay? Pakiran nga, class. And the null hypothesis is that the residual variance is constant or homoscedastic. Sige nga, class, pakiran yan. NCV, non-constant variance test. With the null hypothesis that the residual variance is constant. Okay, what's the result, class? Based on our statistical test, is our residual variance homoscedastic or otherwise? Answer, please, class. Type 1 if it's homoscedastic, type 2 if it's heteroscedastic. So type your answer, class. Okay, any answers? Okay. Homoscedastic, Friedrich. How about the others? Thank you, Friedrich. Let's wait for the others to key in their answers. One, Abigail, homoscedastic then, Quina. How about the others? Okay, sige. Glenn, Gianna, thank you. I hope the others are able to get this, no? So let's run this. And, okay. So the p-value is practically less than 0.05. This is practically 0. No? This is significant at 0.001. So our null hypothesis is residual variance is constant. With a p-value less than 0.05, we reject the null hypothesis. No? So the answer should be number 2. Hindi homoscedastic yung yung ano natin, yung residuals natin. And that's confirmed by the visual. Diba? Take note class, no? Ang null hypothesis is homoscedastic yung residuals, residual variance. It's not homoscedastic. Kasi we will have to reject that null hypothesis with a p-value less than 0.05. All right? Okay. There are other test class. Ito naman, ito, familiar din to. Ito yung isa sa pinaka-popular, no? Itong Bruce-Pagan test. Let me share this with you. Okay. So si Bruce-Pagan test, popular test to ng heteroscedasticity. Okay. By the way, class, going back to our reference a while ago, dito may mga ibang test pa, no? Yan. So, for example, here, ayan, no? May GQ test pa. For heteroscedasticity. Here, okay, explanation lang to. Okay, so kasi ano to kasi stata siya. Okay, all right. Anyway, so let's go back here. So si Bruce Pagan test class, anong tinetest nito? Okay, ang ginagawa nito class, it will create a regression model, kukunin yung residuals and then square niya, and then i-regress dun sa i-regress dun sa mga predictors ng model. Si model, di ba, 4 na predictors yan. So instead of the hourly wage, ang i-regress niya yung residuals and then i-square nun. Okay, tapos kukuha ng ng ANOVA, tapos using chi-square test malalaman niya kung may significant predictor dun sa kung may overall goodness of fit. Okay? So, ito lang yung class, no? It's from the LM test, linear model test package. Okay? So, I think we already loaded this before. So, you can use library LM test or just use this namespace here, LM test. Okay? And if we run this, pareho lang class yung no? Pareho lang yung null hypothesis natin dito. Here, okay? The Bruce-Pagan stat is 43.44. P-value is practically 0 also. Okay, so we also reject the null hypothesis that our residual variance is homoscedastic. So true enough, based on the NCV test and the Bruce-Pagan test, heteroscedastic yung Tapos meron pang isang class, si White's test. Actually, hindi lang isa, may iba pa. So I'm just sharing with you other tests here. Si White's test, which is, sabihin natin, mas, I would say, mas comprehensive kaysa kay Bruce-Pagan test. Kasi dito class, tingnan nyo to Okay. So we have here, okay, I'll discuss this, itong interaction, no? Okay. So in the meantime, okay, wag nyo muna intindihin tong no? Tong, let me share this with you. Yung code na to, okay? Kasi it will mean that we will have to understand itong I na to, no? This is interaction. Okay? So this means that yung predictor natin is fitted values ng model and then ini-square natin siya, no? Okay. Fitted values plus the the square of fitted values. All right. So if I run this, okay, ang lumalabas dito class na, okay, p-value is really less than 0 then. So pareho lang din, no? So in this instance, si White's test at saka si BP, Bruce Pagan test, parehong result ang linalabas na heteroscedastic yung yung residuals natin, yung variance ng residuals. Okay, because sometimes they can conflict. Pwede mag-conflict si Bruce Pagan at saka si White's test. Okay, and then there's another test here. May iba pang test, no? Gold quant test. Okay, but this is sufficient for us here from the performance package. So you have to install that packages and then performance, or you can just directly uh, check nyo nga class kung magra-run sa inyo to. Performance and then check heteroscedasticity ng model natin. So let me, in the interest of time, I'll chat this. All right, let's run this. Okay, so ang sabi dito, warning, no? Heteroscedasticity, non-constant error variance detected, P less than 0.001. Okay, so there's this warning that yung residuals natin, hindi siya homoscedastic. Okay, and we said, class, that ano kung homoscedastic yung, heteroscedastic yung residuals natin, hindi na blue yung natin, yung model natin. Okay, unbiased pa rin yung parameters natin, pero yung standard errors natin, biased na. No? Okay, so pag bias na yon, kung hindi na tama yung standard errors natin, mali na rin t-stat natin, mali na rin yung yung p-values natin. So hindi na tama yung possible na hindi na tama yung inference natin. Kasi inference natin will be based on the p-value. Okay? All right. Any questions so far, class, about itong heteroscedasticity? Kindly chat, please, class. Any comments about that? Clear ba tayo so far? Okay, let's wait for a few more of your classmates, and then we move on to a normality of residuals. Okay, thank you. So far we have looked at the linearity assumption, the assumption that your residuals are homoscedastic, the residual variance is homoscedastic. Then we have another assumption, yung distribution ng residuals. Okay, so this is another assumption that the residuals are normally distributed. So we can plot the second one, okay? And here, your residuals should follow as close as possible to the QQ plot, no? Ito, class, yung line na to. And you can see here that yung mga end values ng natin, yung sa residuals natin, the higher residuals class, ayan, dito naman sa outliers. So may problem tayo, parang may problem tayo sa sa normality ng residuals natin. Okay, so just like a while ago, ano naman kung non-normal yung natin? Okay, so let me share this with you. Okay, and okay. So I provided here, class. Tingnan natin to in a while lang. So pag na-violate yung normality ng residuals natin, okay, pwedeng magka-problem pag small samples. So if we have small samples, yung confidence interval natin at saka kasi yung p-values natin, it relies on normality assumption. So kung mali, class, kung hindi normally distributed yung residuals natin, then magkakaproblema tayo dun sa sa p-values, and then so pwedeng mali yung natin, magiging mali yung inference natin. Okay? However, class, ito yung caveat natin. In large samples, okay, large samples, at least 10 observations per predictor. So kunyari, if we have 7 predictors times 10, so dapat 70, no? So dapat at least 70 yung ano natin, yung observations. Okay? Pag large samples daw, hindi masyadong issue yung normality. Okay? Although itong at least 10 observations per predictor, according to Smith and Finan, ano siya, no? It's just a rule of thumb. Okay, rule of thumb lang siya. Okay, let's go here. Okay, let me share this with you. This is a very good discussion on normality. Control C. This is an article, no? Dito ba siya? Hindi. Sorry. Okay, open yan. Ito class, no? Yan. So this is an article. Pero you may downloadable ba to? Hindi yata, pero pwede mong i-ano to, class. Doon kayo mag-research sa ProQuest natin, makukuha nyo to. Okay. So what is this research all about? So researchers often perform arbitrary outcome transformations. Okay, so anong ginagawa daw? To address normality, ang ginagawa, tinatransform yung data. Tinatransform yung dependent variable. So, anong ginagawa? Log transformation. Kung hindi normally distributed yung ano natin, yung dependent variable, ano gagawin dyan? I-transform, pwedeng kunin yung log, pwede tayong mag-power transformation. I-raise natin to a certain power. Pwedeng more than 1, pwedeng less than 1. Pag less than 1, root yun, di ba? Okay? Now, itong article na to, ang sinasabi nito na baka unnecessary na ano ka pa, na magta-transform ka kung hindi normally distributed yung, let's say, yung dependent variable natin. Okay? Sabi that in large data settings, yung transformations na yan are unnecessary and worse, may bias model estimates. Baka maapektuhan pa yung ano, hindi na maging blue yung ano pag nag-transformation ka. Okay, so this is importante sa kanila to sa medical research ano kasi siyempre yung difference nila. Mga researches conducted in the medical or health sciences. Okay, so ano yung result ng study nito? Although outcome transformations bias point estimates, so sabi dito, no, pag nagtatransform tayo ng data, pwedeng maging bias yung estimates. Violations of the normality assumption in linear regression analysis do not. So sinasabi pa nga niya na pag nag-transform ka ng data ng, let's say, dependent variable, kasi hindi normally distributed yung ano mo, pwedeng mabias yung ano mo, maging bias yung estimates mo. Pero kung hindi mo i-transform, tapos kahit na na-violate niya yung normality assumptions, okay lang yun kasi pwedeng hindi mababias yung estimates mo eh. Okay? The normality assumption is necessary to unbiasedly estimate standard errors and hence confidence intervals. Okay, so kailangan daw yung normality assumption para hindi maging bias yung, parang ganun din sa heteroscedasticity, no? Para hindi maging bias yung standard errors. And we know what happens when the standard errors are biased. Okay. Ano yung conclusion nila dito? Take a look at the conclusion. Sa ano kasi, sa modern healthcare, importante ito eh. So ang sinasabi dito, na kung yung research include thousands of data, so malaki yung data, no? Hindi na kailangan kahit na ma-violate ng normality assumption, okay lang, no? Okay lang. Instead of focusing on the normality assumption is often unnecessary. And kahit na i-transform yung data, hindi naman mag-guarantee na magiging valid yung results. And worse, it may bias estimates. Okay? Alright, so itong ano so take note of that, be aware of that, na kung may violations ng pwedeng i-cite to, no? Itong study na to ni Smith and Finan. Alright? So, oops, okay. So let me just, na-share ko na ba sa inyo to, class? Na-share ko na, no? Alright, so i-check natin ano yung test kung normally distributed yung residuals. Okay. But take note, class, take note. You can lean on an article that states that marami pang ibang articles yan. Nagsasabi na kung may violations ng normality, okay, if the sample size is big, no, then hindi na siya masyadong magmamatter. Okay, so tingnan natin, class, yung yung model natin. Ang suspicion natin hindi normally distributed to, no? So i-run natin tong Shapiro test, and then the p-value is less than 0.05. Okay, and what does this tell us, class? We reject the null hypothesis that the residuals are normally distributed. Yan. So si Shapiro test, pinakita sa atin na hindi nga normally distributed yung residuals natin. Okay? Tapos isa pang test, class, ito. Okay, so let me share this with you. There are other tests here. Okay. May mali dito, no? It's almost time, class. So we will end in this. At least umabot tayo sa normality. And that's good. All right. May dito, class, yung huli ang mod 2. Okay. Sige. Let's go here. So I already discussed Shapiro test. May iba pang test, no? Si Kolmogorov-Smirnov. Ganun din to. Ganun din to yung test na to. So this is the code. KS.test, yung residual, P normal, then pinapakuha yung mean ng residual natin at saka yung standard deviation niya. So ang inaano dito, class, yung Kolmogorov-Smirnov test. And again, the null is similar to the Shapiro-Wilk test a while ago. So i-run ko to. Okay. So ganun din, class, ang sinasabi, no? The p-value is very, very small. Okay, so ang sinasabi natin, we reject the null hypothesis that the residuals are normally distributed. Okay, so whether we're using Shapiro-Wilk or Kolmogorov-Smirnov, Shapiro, maiksi lang yun, Oh, ito lang, Shapiro that test. I want you to write it, no? Kayo na. Ito, i-share ko sa inyo kasi medyo mahaba, no? Ito, Shapiro that test lang yan. Then the residual of the model. Okay? All right, then this one. No? Meron pang ibang mga test, no? Like this one. Okay, ito magandang test to, class. This is coming from your OLSRR. OLSRR. So si OLSRR, hindi lang yan for stepwise regression. No? It can be used also for diagnostic test. Okay, run natin to. Okay, ang sinasabi niya dito, here are several tests. Ang nakita lang natin si Shapiro-Wilk at saka si Kolmogorov-Smirnov. May iba pang test, yung Kramer at saka si Anderson. Pare-pareho yung null hypothesis niya. And all of them give p-values that are less than 0.05, which means that all of these tests reject the null hypothesis that so ang question dito, do we need to do all the diagnostics? No. For each model, hindi na. For final model na, no? Glenn, yung question ni Glenn dito kasi, for each model in the stepwise, hindi. Hindi. Kaya nga, klase din natin ginawa yun kasi I was waiting for the final model. Doon na sa final model magda-diagnostic test. Otherwise, kada stepwise mo, di ba? Diagnostic ka, hindi naman ano yun, hindi naman tama yata, no? Alright? So ito yung ano, no? Ito yung isang test na to. And then you can plot the although plinat na natin to, no? OLS plot residual ng model natin. Okay? Ito na yung kanina. No? Similar lang siya. Yung plot which is equal to 2 natin. Yan. And then, if we base it on a histogram, makikita natin talaga na okay, may steep values tayo dito. Yan. Ito yung normal distribution. Tapos ito yung mga values ng residuals natin. Okay? So makikita natin na hindi siya normal distributed. Alright, and then this last one, yung correlation sa mod natin. Okay? OLS test correlation. Okay, so ano ibig sabihin nito, class? What's the meaning of this? Okay, so I'll leave you guys to see what's the meaning of this last one. Okay, correlation lang naman to ng observed residuals at saka ng expected residuals under normality. Okay. All right, so next meeting, class, we're going to now go to the fourth assumption. Ito na yung ano, dito na tayo papasok sa walang outliers. So dito di-discuss natin si DF fits at saka si Cook's distance. Okay, in the presence of outliers. All right, then we're going to go to specification bias. Paano kung may missing predictor? Titingnan natin 'yon, no? Next meeting. Plus, and then we'll wrap this up. Okay. Wrap up by looking at remedies dun sa ano. Kasi kita natin may problema tayo sa linearity, no? May problema tayo sa heteroskedasticity. May problema din tayo sa normality. Yung normality, medyo pwede nating in fact, dun sa Gauss-Markov, hindi naman siya kasama eh. Originally, hindi siya kasama sa Gauss-Markov assumptions. So yung normality class, pwede nating ma-justify yan kasi medyo large naman yung data natin, 526 observations tayo. No? So based on that study by Finan. No? Okay, so let me